In the last video, we started talking about equations like these. D squared y over dx squared plus 9y equals 9x cubed minus 3x. So we started talking about equations like this, where on the left-hand side we have just a sum of constant multiples of y or its derivatives, and on the right-hand side we have some function of x. Last video we explained that a good technique for solving these is to split it into two problems. Firstly, you find one solution of this, the particular integral, and then secondly, you look for solutions, the so-called complementary functions, where this left-hand side is equal to 0, and you add the two together. So you add the particular integral to the complementary function to get the general solution. In this video, we'll just be doing this example and another example where finding the particular integral is just a bit more complicated. So it's a good idea when trying to find a particular integral to look for something that's a bit like the right-hand side. So when we look at this, we might have the idea of trying y equals x cubed, because we can see that 9y will give us 9x cubed, and the second derivative of x cubed will give us something linear in x. So at least we'll be kind of close. So we get d squared y by dx squared minus 9y equals, well, the first derivative of x cubed is 3x squared, so the second derivative is 6x. Oh, should be a plus sign. So we get 6x plus 9y, which is 9x cubed. That's pretty close, except we want minus 3x rather than 6x. So we might think about correcting it by adding on some multiple of x, then the 9y will give us what we want, and differentiating the multiple of x will be 0, so that won't change that term. So if we try y equals x cubed minus x, then we get the left-hand side, d2y by dx squared plus 9y, is equal to, well, the second derivative of this is 6x minus 0, and 9 times this is 9x cubed minus 9x, and that's equal to 9x cubed minus 3x, which is exactly what we wanted. So this is one solution to this differential equation, so we found our particular integral. Now we just have to find the complementary function. So we have to solve the differential equation we get by setting the right-hand side equal to 0. So we have the left-hand side equals 0. So this is a homogeneous equation. We've spent several videos working out how to solve these. The way we solve it, of course, is we produce a quadratic equation arising from trying y equals e to the kx. And the quadratic equation here is k squared plus 9 equals 0, which has solutions k equals plus or minus 3i. Now, we could write our complementary function in the form y equals ae to the 3ix plus be to the minus 3ix. That would be a perfectly valid way of writing the complementary function. But as in past videos, we don't really want these complex numbers floating around, so it's probably better to use de Moivre's formula to write them in terms of cos and sine. Of course, when we do that, e to the 3ix will be cos 3x plus I sine 3x, and e to the minus 3ix will be cos 3x minus I sine 3x. So we can get y equals any constant we like times cos 3x plus any constant we like times sine 3x. That's our complementary function. So the general solution is what we get by adding the particular integral to the complementary function. So the general solution is y equals x cubed minus x plus c cos 3x plus d sine 3x. So the general solution is the particular integral plus the complementary function. And this gives us a two-variable family of solutions because we can take c and d to be any constant we like. So that's one example. Let's do another. That example we've just done and the example we did at the end of the last video both had polynomials on the right-hand side of our differential equation. We're going to do an example where we have an exponential function on the right-hand side instead. Let's do the example d squared y over dx squared minus 6 dy by dx plus 9y equals e to the x. Now, this is very different. We have an exponential function on the right-hand side, but the idea for solving it is the same. In order to find our one solution, our particular integral, it might be a good idea to try something pretty similar to the right-hand side. So let's try y equals e to the x. Well, what do we get then? Of course, dy by dx, the derivative of e to the x, and indeed the second derivative of e to the x, are both still equal to e to the x. Differentiating e to the x doesn't change it at all. So when we substitute this into the left-hand side, we get e to the x minus 6e to the x plus 9e to the x equals 4e to the x, which isn't quite what we want. We wanted e to the x on the right-hand side, we've got 4e to the x. But I think it should be fairly clear what we should do now to mend that. What we should do is try y equals a quarter e to the x. Then, when we look at the left-hand side, we get e to the x over 4, minus 6 times the derivative is minus 6e to the x over 4, and plus 9 times e to the x is plus 9e to the x over 4. And now we have e to the x plus 9e to the x minus 6e to the x, which is 4e to the x all over 4, so that's just e to the x. Exactly what we wanted. That means that our particular integral can be taken to be a quarter e to the x. Now what we need to do is find the complementary function. So we want to solve this left-hand side equal to 0. So we want to solve second derivative of y minus 6 times the derivative of y plus 9y equals 0. As ever, we do this by guessing y equals e to the kx and forming an equation to find out what k must be. The equation, of course, will be k squared from here minus 6k from here plus 9 from here equals 0. We can factorise that by sight. It's the k minus 3 all squared. So this quadratic has a repeated root. It's got 2 roots at k equals 3. So if you remember from an earlier video, the right way of dealing with this is to try solving it with not just e to the 3x, as our guess would cause us to suggest, but also x times e to the 3x. So that's our complementary function. And our general solution is the particular integral, that one solution we found at the beginning, plus the complementary function, which is the general solution into the homogeneous version of the equation. So the general solution is just those two added together. So that's y equals a quarter e to the x plus a e to the 3x plus bx e to the 3x. Or if we prefer, we can group the two e to the 3x's together and so write it as a plus bx times e to the 3x. So while the details are very different, once again it turned out to be a good idea to guess particular integrals that look a bit like the right-hand side. We'll do a bit more of this in the next video.